So the last colligative property that we'll talk about is osmosis. So what exactly is osmosis? Osmosis is defined as the movement of solvent across a semi-permeable membrane towards the solution with a higher solute concentration. So what does this mean at all? Well, let's look at an example. So here we have a tube. There's a U in it, and both sides have liquid in them. And at the very bottom here is a membrane that allows solvent molecules to move through, but it doesn't allow solute particles to move. There are such membranes that allow liquid to flow through, but don't allow dissolved solids or other species to traverse through them. So it's semi-permeable. And on one side of the tube, there is just pure solvent, just water. And on the other side of the tube, there is a solution, maybe salt water here. Osmosis is the process of solvent from the pure side moving towards the solution that has a higher solute concentration. So it's moving from left to right. What results from this then is a difference in the height of the two solutions, because we've lost solution from the left side and we've gained it on the right. And as a result now, there's actually a pressure difference between these two solutions. Remember back to our talks about manometers. We now have a difference in the height in the tube, so we have a pressure difference there. And if we take a piston and we apply pressure on the solute side, in order to force solvent molecules to go back and re-equilibrate the levels of the two solutions, the amount of pressure that we apply is referred to as the osmotic pressure. And it's given this Greek capital pi symbol. Now, just like the other colligative properties, there's an equation where we can calculate osmotic pressure and relate it to solution concentration. So osmotic pressure here is pi is equal to I mRT, where pi is the osmotic pressure, I is still the Van 't Hoff factor, it's the number of solute particles per molecule. And M is now the molarity, not the molality. In this case, we're using molarity, and R is the gas constant. So since we're dealing with pressure in this case, we've got concentration and the gas constant present. T here is the absolute temperature, just like when we were dealing with gases. This has to be in Kelvin. So what does this look like, and could we do an example of osmotic pressure? Osmosis is a really, really important principle. It's used in water purification. It's used in dialysis for cleaning blood for patients that whose kidneys no longer work well on their own. It's used in a host of things, just as many of the other colligative properties have real-world applications. Osmosis is very important. So what does this look like? Well, here let's say that we had a dilute solution of some water-soluble organic compound that's prepared by dissolving 2.35 grams of that compound in water to form a 0.25 0.25 liters of solution. So we took 2.35 grams and dissolved that in water up to 0.25 liters. And the resulting solution, if we put it into one of these tubes and into a machine that would measure the osmotic pressure, is 0.605 atmospheres at 25 degrees Celsius. So assuming that the organic compound, whatever it is a non-electrolyte, meaning it doesn't break up into ions, and we could certainly measure this maybe by simply measuring the conductivity of the solution. What is the molar mass of that organic compound? So I'll look at my equation and just list out the stuff I've been given. I've been given pi, the osmotic pressure. I know since osmotic pressure has been given to me in atmospheres, I'm going to use the gas constant that involves atmospheres. So that's 0.08206 liter atmospheres per mole Kelvin. And temperature has to be in absolute Kelvin, so that's 298 Kelvin by adding 25 to 273. Now, if I look at my equation, pi equals I mRT, and rearrange to solve for the concentration here, because I know pi, I know I know R, and I know T. I'll rearrange this to solve for the concentration. And if I plug the values in, I come out with molarity as being 0.0247 moles per liter. And why exactly do I need moles per liter if I'm trying to get to molar mass? Well, I have a concentration and I have a volume. This will allow me to calculate the number of moles of that organic compound that's present in the solution. Once I know the number of moles, I also know the mass of the organic compound that I dissolved, and molar mass is simply grams divided by moles. So here I take my molarity, multiply that by the 0.25 liters, the volume, and come out with 6.185 times 10 to the minus 3 moles. And then I take the grams of the organic compound divided by the moles of the organic compound, and I'll come out with a molar mass of 380 grams per mole. There's certainly many other applications. We could solve for osmotic pressure. We could even solve for I if we needed to in various applications. But this is how we relate osmotic pressure quantitatively using the pi equals I MRT equation. And this is the last of our colligative properties that we'll talk about for chapter 13.